And we now have the second lecture by Nikita Nekrasov.
So yesterday we were talking about simple classical things. Today we'll go to more complex things. And then the day after tomorrow we'll start quantizing and dualizing and do other things. So today we'll complexify. So complexification is it's a process, it's an art, it's a mindset. So R becomes C. Z2 becomes, well, depending on how complex you are, could be U1, could be C star. And so classical. So what happens to classical mechanics? Here we have options because yesterday, remember, at some point we were discussing that we're discussing paths, spaces of paths in phase space, and we would like to complexify the space of paths in phase space, and so one way to do it is to complexify the phase space, but keep the paths real. So if I denote my phase space by P, I'll make them into paths in the complexification of the phase space. And so what's the complexification of phase space? That's complex manifold with holomorphic symplectic structure. So this is so it's a 2-0 form, which is closed and non-degenerate. So why do that? There's various reasons to at least think about it. One is to make use of complex analysis. So even if your original problem is very real, involves dynamics in real phase space, you might want to do statistical mechanics when you integrate over the phase space some measure. Probability measure may be induced from Liouville measure, and the Hamiltonian, but you're interested in integral quantities, in averages. Now, to compute an integral, you don't have to integrate over the space you are given. You can use Stokes' theorem and deform your integration contour. And so then, more often than not, you end up integrating over contours in the complexification of original space. Yes, Conor. You see, that's good. Yes, that's the thing. So real paths. So because what is time? Time is a way of okay, I'm not going to talk about what is time, but time is just a label. Time is just a label, and so I label points in my phase space. Now I want to make this space of this path a complex space. It just means that I make my target complex. It's a literal complexification of the space of paths. Now, there is another approach. So this is a bifurcation. Take complex paths in the original space, this is where string theory starts. So you replace word lines by word sheets, and that gives you another way of kind of complexifying the problem. We will find eventually, maybe if time permits, that these things are actually related. That if you really try to, when you really start approaching, especially the approaching quantization as a study of periods, you will end up studying not just paths, but maps of high-dimensional objects into the phase space. But we'll get there in due time. So now that this simple process kind of allows to freely talk about things which otherwise are hard to discuss in full generality. And that is, so let me continue now with my example of the many-body system. Which I want now take to be elliptic. So I will write the Hamiltonian as I did yesterday. Again, maybe with the same mistake I did yesterday. But now I will generalize the potential, which was the rational or trigonometric function with the second order pole at the diagonal, to an elliptic function. So this is Weierstrass a function on some elliptic curve, which so it's a function which has two-dimensional lattice of periods, and the parameter which characterizes this lattice, tau, is a complex number with a positive imaginary part. And unless you make tau very special, like purely imaginary, this function is not real on the real axis. And so it would make the dynamics formally defined by this Hamiltonian look awkward unless you allow P and X to be complex valued. So I mean, just thinking about this problem makes it natural to allow I mean, I wish I knew. Okay, so it is natural to allow P and X to be complex. Okay, maybe I should be careful. But then an interesting phenomenon happens. Now it turns out that the fact which on the real axis, so when P and X were real, and you studied the configurations of finite energy, and so it was obvious that for the real function, you cannot let points collide because that would require infinite energy. Once P and X become complex, you can actually keep the energy finite by allowing particles to approach each other by making the momenta very large and complex in such a way that the potential compensates the kinetic energy. So the phase space is actually more interesting, and so it's we can take the cotangent bundle to this elliptic curve to the power n, I will not delete diagonals. I will divide by the symmetric group, and then I will resolve the singularities of this symmetric product. So it is actually a smooth hyperkähler manifold. Hyperkähler in this context means that I mean I did not introduce enough data to really appreciate what it is. It means that in addition to the symplectic form, which is in these coordinates, which are not the global coordinates, it's just dp dx. It also has a metric. Say it again. Sorry, what is n is I1 to n. Yeah, well, if n is equal to 1, then you just take t star of e. If n is equal to 1, there is no potential. It's just one part. So if n equals to 1 is also true, but it's kind of trivial. So your phase space is just t star of e. And the Hamiltonian is just one half p squared. Okay? Yes? No, it's a parameter. So tau is a parameter. Just like nu. So nu is a coupling constant. It's a parameter, and tau is also a parameter. Just the model has some parameter. So there are different physical contexts in which this arises. You can say that your particles still live on the real axis, on a circle. So there is a, okay, now I can get to use the color chalk. So inside this elliptic curve, there is an actual real S1. And of course, classically, if I put initial, okay, so this is now. So if I start with the configuration of points which are real, which all belong to this circle, and put some initial conditions for momenta, let's say also real, then for tau complex, the Hamiltonian will force these particles to move around, so they will not be confined to the circle. But you can still restrict your motion by forcing, by somehow adjusting momenta so that the coordinates continue to be real. And so you can, so when you quantize, you can look for, so if we write, so in quantum problem, we would make out of this function a differential operator. So the operator will be acting on functions, some kind of functions of x. And even though the functions will have some, they're analytic, so they're defined on in some neighborhood of this circle, you can restrict your functions by requiring that they're normalizable only when x is on the circle. Nevertheless, you don't have to restrict tau to be purely imaginary, so that the Hamiltonian will have in general, so this operator H2 hat, which is H2. will have in general complex eigenvalues. As functions of nu and tau. So you can make both parameters nu and tau complex. So what is not quite trivial and interesting is that on this true phase space, the symplectic form omega, despite this formula, despite the appearance that it looks like an exact form, is actually not exact. So these coordinates p and x are not the global coordinates. They don't cover everything. And so this form has a non-trivial cohomology class. Is not, no, it's not exact. It's not exact. It's not exact. It's non-trivial in cohomology, and so there is a real two-dimensional sphere inside the space, such that the period of this form is proportional to nu. And so the coupling constant, the coefficient in front of the potential term, actually measures the topological non-triviality of the symplectic form. So there is this 2 which arises because of this resolution of singularities. Maybe we can discuss the case n equals to 2 to see how it comes around, how it comes about. So let's take n equals to 2 case. So we'll, and let me, for simplicity, just restrict to the so-called center of mass. Frame. So it just means that we, in the language of yesterday, we perform the symplectic quotient. So this phase space is acted by the group. The group is actually the elliptic curve itself. So this group acts by shifting all coordinates by the same amount. So this transformation doesn't change the Hamiltonian. And the moment map for this, the momentum map in this case is precisely the momentum. It's just the sum of all coordinates. So we can, as an exercise, we can perform the reduction by fixing the momentum to be 0 and identifying configurations of points related by the overall shift. Yes. Yes. That's why we're going through this example. Yes. This is, it's, you see, the point is that, okay, we will go through example, but I just want to repeat what I said. What I said was that the coordinates p and x don't cover the whole phase space. You add something to the phase space while keeping the fact that the Hamiltonian is well defined. So you can allow x1 approach x2 at the same time p goes to infinity in some way, yet the Hamiltonian is fine. Yes, nu is determined uniquely. Yes. What do you mean? What do you mean uniquely? Nu is I just wrote nu. I mean, how does this? Oh, nu goes to minus nu. I mean that's the question.
I mean, this integral. How does it know about Hamiltonian?
Okay. The fact the way I resolve the singularities of this symmetric product produces a manifold which has a complex structure which depends on nu. So okay, so the phase space, this reduced phase space, the reduced phase space in this case is the quotient of the cotangent bound to elliptic curve. Elliptic curve here is just being, let's say, x1, so it's x1 minus x2. This is the coordinate on this elliptic curve. This is the invariant under these transformations, and Z2 exchanges x1 and x2, and so it maps x to minus x, but it also acts on the momenta, so because this exchanges momentum P1 and P2, and so let's say, so this is how my group acts. So so there is a naive phase space which is just a quotient of the cotangent bundle to the elliptic curve by the involution which changes the sign. So that involution has fixed points. And now each fixed point locally, first of all, do we know how many fixed points does it have? Because I said so. Okay. Let me erase that. I'm supposed to go from left to right. Four. Good. Very good. Indeed, it has 4 fixed points. So, okay, so this is my picture. So the elliptic curve has 4 points on which the involution x to minus x, which are fixed under this involution. So these are the points x equals to 0, 1/2, tau over 2, and 1 plus tau over 2. And then we have a fiber of the cotangent bundle. And so so in this fiber, the involution also acts by changing sign. So the 0 in the fiber times this point are the fixed points. So let me look at this fixed point, and then it will be easier to will be analogous at other fixed points. 4. P. So P goes to minus P minus X. So we have, so X is defined up to the shifts by integers and integer multiples of tau, but P is defined as it is. So the only way to be fixed is to set P equals to 0. Yes? You heard what? Sorry. So the right, but okay. As Senya would say, this is not a question. So. Yeah, it's more subtle than that. Of course, 16 is a number of fixed points of the involution acting on the 4-dimensional torus. So if you try to make elliptic both coordinates and momenta, this whole phase space now is built out of the abelian varieties of dimension 2. And so then it's then 16 is important because that's how you make K3. So then, so what I'm presenting to you is the baby version of K3 manifold. But the special feature of this story is that the local geometry near each of these fixed points is identical. In general, in general, this space has more complex deformations than are available to us. You can, so at each of these fixed points, so this is the local picture. I will explain why I write them, I draw them this way. So you can resolve singularities by gluing in a two-dimensional sphere at each of these points. And in general, you can make the spheres be completely independent of each other. So you would have four-dimensional space of parameters, but this will not be related to the integrable system which we're discussing. So for K3, for example, each of these 16 fixed points on the four-dimensional torus comes with its own parameter, and that's why K3 eventually has lots of complex deformations. In our case, we have more symmetry, and so we have only one deformation accessible to us, available to us. So let me just discuss what's going on locally. So locally, we can model this on C2, on Z2. So C2 is also a complex symplectic manifold with symplectic form dZ1, dZ2. And so I want to consider the orbifold of C2 by the cyclic group of order 2, which changes the sign of both coordinates. So algebraically, the quotient is the spectrum of the ring of invariant functions. And so what are the invariant functions? The invariant functions are the product Z1, Z2, Z1 squared, and Z2 squared. Right? So these are, so any polynomial in Z1 and Z2 which is invariant under the simultaneous changes of coordinates can be expressed as a polynomial in these three variables, but they're not independent. And so there is a relation, namely if I take the product of YZ, I get X squared. And so this equation describes a cone in C3, and that's why I drew this quotient as a cone. So this cone is the X squared equals YZ in C3. Now you can essentially you can blow up the singularity and describe it as a so we can blow up and make it into the total space of O minus 2 bundle over P1. And so there will be a non-contractible two-dimensional sphere inserted in place of the singular point of the cone. But you can also do a complex deformation. And so complex deformation just one second, is the same thing, but if you look at it from a side, so to speak. So complex deformation is just adding a constant here. So this is now a constant, a parameter. Yes, what's the question?
Why are we making this blow up at 4 points? Why not make the pole of the wave
So this is where. So for the moment, I'm just looking at the geometry of this space. I'm not paying attention to the function itself. The Weierstrass function actually behaves differently at this point. So it is singular at one of these points and is non-singular at other points. So indeed, that's going to be important. But I just want to discuss how is it, how is it this local geometry changes when we resolve the singularities. And so this is not a resolution, this is deformation. Now, if you think about this complex surface as a real four-dimensional manifold, you can actually, it has many complex structures. And so what looks like a blow-up in one complex structure will look like a complex deformation in another complex structure. And so from the real geometric point of view, these are all equivalent procedures. And so what this procedure does, it replaces this space by a new space. So now it's a non-singular quadric. So now we can look at this two form, which in these coordinates would be expressed as dy, for example, dz divided by 4x, right? And now I keep this form, but I deform the relation between x, y, and z. So now it happens. It turns out that this form has a non-trivial period. Because let me write this. Let me rewrite this equation as follows. Let me say x is zeta times little x. Y is zeta times y plus square root of minus 1z, and z is negative zeta y minus square root of minus 1z. This is just a parameterization. So now this equation becomes simply that x squared plus y squared plus z squared is equal to 1. So it's the equation of the sphere, but it's actually a complexification of the sphere. So it's so there is a real sphere when x, y, and z are real, and so that's the non-contractible S2 which I promised. But since I'm just making a change of variables, x, y, and z have both real and imaginary part. So what displays. No, differential of omega is 0. Differential of omega is 0 because x, y, and z have a relation. So this is yes. Okay. So this form is okay. I will not be very specific, but it would look like dx dy dt over x. Maybe there are some square root of minus 1, maybe over 2. So now I claim that if I restrict this form on a real sphere, so this restricted on S2, which is defined by the equation that x, y, and z are real, this is just a volume form. Just a volume form on a two-dimensional sphere. Just write it. So x is cosine theta, y is sine theta, cosine phi, z is sine theta, sine phi. So this will be just the standard volume form. And so it has a non-trivial, famous non-trivial period, which is 4 pi, I guess. And so this form therefore has a non-trivial period proportional to zeta. Okay, so going back to this case, this example, n equals to 2. I want to do the similar analysis with this invariance, but now it's directly in the elliptic case. So if I have two variables p and x, but now x is elliptic variable, so it's defined up to the periods, and I want to make a quotient with respect to the symmetry. What are the invariant functions on the space? I'm allowing functions which have poles in x, otherwise we would be without functions because the elliptic curve is compact. So one function which is famously invariant under x going to minus x is the Weierstrass function. So it is. I should have written the formula, by the way, for pay. I mean, if we start with simplicial complexes, that maybe we need a formula for pay function. Yes. Because that's a symmetry. It's a symmetry of the Hamiltonian, and it's a symmetry of the symplectic form. There's also a constant which I don't remember. Plus a constant, which is usually chosen so that the expansion of this function near 0 starts at x squared term. So there's no constant term. So my Hamiltonian in this notation, the Hamiltonian is essentially p squared plus nu squared p function of x. And so it has a symmetry which changes the sign. The Hamiltonian itself, of course, has a symmetry which changes separately the sign of p and x, but it's not a symmetry of the symplectic form. We have a symplectic form. So if I change the sign of x, I want to change the sign of p. Otherwise, I'm not. Okay, so let me call this function capital X. So this would be the analog of, I think, what I called y. Now, there's another function. So if I take the derivative of the pay function, it is, so if since pay is an even function, the derivative is an odd function. So I can multiply it by p and produce another invariant function. So I apologize, it will be slightly different. Let me call this x1. Okay, call it x1. That I will call capital Y. And then there is another function, p squared. So let me call it x2. So here I got myself another three invariant functions, and every invariant function of p and x, which is meromorphic with respect to x, will be a polynomial in these three functions. But again, as before, they are not independent. And so, what is the relation between them? Well, let's compute y squared. So y squared is p squared times the square of the P function, so P squared is x2. And the square of the P function is a cubic polynomial in x1. So this is 4x1 cube minus g2 x1 minus g3. So this function solves the KdV equation, which is when G2 and G3 can be explicitly computed so the way to prove it, you expand left-hand side and right-hand side and x near 0. You make sure that all singular terms agree, and then the left-hand side minus the right-hand side has no more singularities on x. Therefore, it's a constant. It's a constant, and if you adjust constant so that then this constant will be 0. So G2 and G3 are expressed in terms of the fourth and the sixth Eisenstein series. All right, so this is the equation which replaces the this quadric which we had in the local picture. Now, if you expand this cubic polynomial in terms of its roots, well, near each of the roots, you'll have the same story, and there is a fourth. So the fourth point, the fourth singularity, which is actually an interesting one for this system, is when x1 goes to infinity. So now so my phase space, if you like, so my phase space is a complex surface which whose affine part. So there is a part of it which is described by this equation, to the extent that this equation is not all of the elliptic curve. So the elliptic curve is compact, and this equation describes the complement to a point. So this is the algebraic curve. So I need to either make projectivitize this equation, right? Make it a homogeneous equation of degree 3, or just say that I'm adding a point. And so when I'm adding some points, I will partially compactify the surface, and the net result, and this is where I'm actually heading, is that right. So this is a complex surface, right? So this is a surface. It's a two complex dimensional manifold, and now I want to represent this two-dimensional manifold as a fibration over one complex dimensional base. So it's a base of complex dimension 1. Fibers, which will be also of complex dimension 1, and the fibers being elliptic curves. But now the complex structure of these elliptic curves will depend on the point on the base. And so I will just massage this equation so that you will see how it goes. Remember that we had the Hamiltonian. So the Hamiltonian H expressed in terms of my invariants is simply x2 plus nu squared x1. Right? So now I substitute this into the equation. So let's say that y squared is equal to h minus mu squared x1. We put 4. And I'm tired of writing x1, so let me erase index 1. So now x is x1. So E1, E2, E3 are the roots of this polynomial. So just like G2 and G3 are Eisenstein series, E1, E2, E3 are some theta constants. They sum up to 0. So now think of this equation as follows. Let me rescale h and call it mu squared times u. So then this will look like 4 mu squared u minus x, and then this thing. And so when I fix the value of my Hamiltonian, of the energy function, the fiber, so this set of all points in the phase space which have the same energy, is a solution of this equation. And now this deformation slash resolution consists of adding a point at infinity. So I'm just adding a point x going to infinity and y going to infinity as x squared separately for different u's. So I'm doing this. I'm doing the opposite to the I forgot what it's called. Reduced suspension, right? So no, I'm not okay. Not that opposite. Not that opposite. I'm making a refined suspension. Refined suspension. So I'm making a suspension, different suspension over different points on the base. Okay. So I'm compacting. Okay. In other words, if I just take this, the affine curve given by this equation, well, so y squared equals a polynomial of degree 4. You know that this is also an elliptic curve, but it's an affine curve, so it's an elliptic curve missing 2 points now. So I'm adding back in those 2 points, compactifying the fibers. So now the complex structure of this elliptic curve depends on u. It depends on the cross ratio . It depends on cross ratio of u, E1, E2, E3. And so it will degenerate. There are 4 points on the base. If I compactify, I can compactify the base by adding a point at infinity. So that way I will make it CP1. And there are points E1, E2, E3, where my fibers degenerate. So all this we see once we complexified the problem, because over different points the fibers degenerate in different ways, and you cannot see that if you only look at the real slice. Elliptic curves behave in a kind of irregular way if you try to slice them with real. If you look only on the real points, but once you complexify, everything becomes regular and beautiful. So the claim is that this structure persists for all n's, not just n equals to 2. But to see that, we need to describe the Lax representation for elliptic Calogero-Moser system, and it was found by Igor Krishchever in 1980. Maybe earlier, but that's where it was published. And by finding this Lax representation, Igor actually discovered what later became known as Hitchin systems. And now, in the framework of these lectures, when things are related to gauge theories, I will present this construction as the analog of the construction we had yesterday for two-dimensional Young-Mills theory, but after we've complexified something. So let me proceed in this way. So I will claim that this is actually kind of a complexification of 2D Young-Mills construction from yesterday. So let me very, very briefly review what we did yesterday, especially for those who arrived later. And I will avoid unnecessary details. So yesterday, we looked at the following infinite-dimensional symplectic manifold. So let me just call it P infinity. It was the space of pairs E and A, where E was the function on circle valued in this simple Lie algebra, or maybe semi-simple Lie algebra, and A was the one form, circle valued in also valued in Lie algebra, and multiplied by a finite dimensional orbit. So okay, so the Lie algebra was actually SUN. The orbit was the n-1 dimensional projective space, and we were performing a symplectic reduction by the action of the group, by the loop of the action of the loop group. So G is SUN, and loops here are again. So these are arbitrary maps of a circle into the group. These are not marked loops. There's no base point here, but the base point appears once I define the action of the loop group. So okay, let me just review the action of the loop group on this data. So G, which is G of X, so X is point on the circle, acts on the pair E A so this is just a piecewise, pointwise conjugation, and this is the gauge transformation of a connection. And now the point Z of the orbit is acted on via evaluation at the marked point. So now we need to mark a point. Maybe I was using inverse. So my circle now has a base point, which I call 0. And so the moment map for this combined action on the cotangent to the to the phase space and this finite dimensional orbit is the covariant derivative of electric field E plus delta function. So it's a distribution supported at this base point, and J is the finite dimensional moment map describing the embedding of Cpn minus 1 into the dual space of the Lie algebra. And this is where the coupling constant appears. So let me write explicitly what is J. So if I represent this point by a sequence of complex numbers whose norm is fixed to be 1, then so this J is mu times Zi Zj bar minus delta Ij. So this is it's a traceless square root of minus 1. So this is traceless anti-Hermitian n by n matrix, which is what an element of the algebra of SUN should be. So nu is gives you the scale of things, and so that's the parameter. And so yesterday what we found was that if you solve this equation and then compute the Hamiltonian, which is the integral of a circle trace E squared, this becomes the trigonometric Calogero-Moser Hamiltonian. So today we'll compactify. So I did not explain what was. So I said that Z2 complexifies into a circle, but I didn't say what the circle complexifies to. And so one way to complexify a circle is to make it an elliptic curve. Yes. It's a point on the projection space. You see, O is Cpn minus 1. So it's a collection. These are n complex numbers. This is the equation they obey, and they're defined up to their overall phase. Okay. So this matrix is invariant under this overall phase rotation. So this is a well-defined embedding of Cpn minus 1 into the space of n by n anti-Hermitian matrices. Yes. So this is all you need to know. So right. So the we derived it yesterday from a longer discussion, but this is all you need to know for the procedure. So we just solve this equation, mu equals to 0, substitute here, and you'll get the Hamiltonian. I want to generalize this now. Okay. Yes. Yes. So you can, okay, very good point. So you can ask what will happen if you move this point in here. Nothing will change. So, but what will change things is that if you add 2 points, 3 points, so you can have many points, that will change the system. So this is what I said yesterday when you said I could have many lines. I mean, we can go there, but I want to briefly explain how this is generalized in this case. So I want to replace the circle by an elliptic curve. So I'm fatten the curve. I mean, fatten the circle. And you have options how to view the analog of this phase space. So the new phase space is now going to be the space of pairs okay, I'll call it E, even though usually it's called phi. So E will be now. It's a bit silly to be Okay. So this is still just a function on, so this is a two-dimensional torus, which has a complex structure, but I'm allowing just arbitrary functions, functions of z and z bar. So these are not meromorphic functions. Sorry, x, z and z bar. So let me distinguish. So the coordinate on this elliptic curve, the holomorphic coordinate will be z, will be denoted by z. So it's a function of z and z bar, function on T2, valued in complexification of my Lie algebra. So it's now valued in SLN-C, Lie algebra. And A bar will be the 0-1 connection. So it's so really this function is actually, it's a 1-0 form, and A bar is 0-1 connection. On this become important when you generalize this to arbitrary Riemann surface. On the elliptic curve, you have global coordinates. You have global one differential, so you can trivialize everything. But what's important is that the gauge group will act in a way which depends on the choice of a complex structure. So now I'm I will explain what this means. So I'm just complexifying ingredients and kind of making it much more expensive in terms of the number of degrees of freedom. Now, what is OC? So OC is a complexification of Cpn minus 1. So so here we had Z, the vector, called Z vector. So Z was in C to the n, and as in Andrei's lecture, so Z was non-zero, considered up to the overall scaling, which I fixed partially by requiring that the norm was equal to 1. So now complexifying this means making Z and Z bar independent. So O of C is now the space of pairs. Z in C to the n, W in C to the n dual, in the dual space, such that the value of W on Z, so this is the analog of this norm, is equal to 1. Up to the scaling. So here we had U1, and U1 becomes C star. One way to complexify U1 is to make it C star. So C star acts simply by scaling Z and W in the opposite way. Okay, so now we can define the analog of J. So make it into a matrix of the form ZIWJ minus W delta IJ times nu, maybe square root of minus 1, but it doesn't matter. So this is simply a traceless n by n matrix, element of the Lie algebra of SLN. And so now I want to make a group of maps of T2 to the complexification of my group. So the group SLN acts on this phase space, and it acts as follows. So I need to mark a point. Let me call it point z equals to 0. And so so now G of Z and Z bar acts on the quadruple E A bar and the equivalence class of ZW by, again, pointwise conjugation of E So here is where we use the complex structure. So we put here the Delbo operator. So I'm only differentiating with respect to Z bar. I'm not touching Z coordinate here. And I evaluate G at its mark point 0. And this is how I act on Z and W. So, so the action at the orbit is by evaluation at this point. So now we need to compute the momentum map and perform the reduction. Okay, I will do it here. By the way, we don't have a clock today. What is the time? Perfect. Okay, so the moment map is, we will compute it maybe in the exercise session. So this is the complexification version of the covariant derivative or divergence of the electric field, plus the same delta function, but now it's a two-dimensional delta function. And so we want to solve this equation and divide by the action of the group. So how to solve this equation? Well, as yesterday, the trick is to find the representative normal form for A bar. So what is the canonical form you can make the 0-1 connection on a trivial bundle look like by performing the complex gauge transformation? So there is a theorem by Atiyah. So it's a kind of complexified version of the Floquet-Lyapunov theory, which says that the generic A bar, can be brought to the diagonal constant form, where alpha i's are now complex parameters and they are constants as Z bar are concerned. So there is a gauge. It's only true for generic A bar. So it means that if you pick one with probability 1, this is true. But of course, you might be unlucky. And if you're unlucky, then something interesting happens, that you can always diagonalize it, but the diagonal components need not be connections on the trivial U1 bundles. So they could have non-trivial first-chain classes. So this is interesting for, actually, this is interesting for applications in condensed matter physics, particularly related to the physics of graphene. But I will not talk about this today. Like, I just wanted to make Pasha wake up. Diagonalize means diagonalize. It means direct sum. It's yes, direct sum of line bundles. So it means that the rank n vector bundle of trivial degree, which A bar represented, generically splits as a sum of line bundles of trivial of degree 0. Okay, and these alphas are, so the alphas represent those line bundles. These are the stable bundles. These are Atiyah bundles. I don't exclude them. I'm taking them. I exclude not Atiyah bundles. Okay. What I said that it's not always true, but this is what I'm going to work with. What, sorry? Semi-stable. Semi-stable. No, this semi-stable. These are semi-stable bundles because they have sub-bundles, obviously. So it's and they slope 0. So they all slope. This is slope 0, and the sub-bundles are slope 0. Okay. In practical terms, all I'm saying is that by complex gauge transformation, I can make almost every A bar diagonal matrix with constant coefficients. And as yesterday, there are remaining gauge transformations of the form, so these are diagonal matrices whose diagonal entries are now periodic functions of z and z bar. So how do you construct a periodic function? So you can either make a combination z minus z bar divided by tau minus tau bar times 2 pi I an integer. So this is invariant under the shifts of z. Remember, we have shifts of z by integer or tau times an integer. So the shifts by integer don't change z minus z bar. Shifts by tau times an integer will shift this whole combination by an integer. So e to the 2 pi I kills that. Or z tau bar minus z bar tau divided by tau minus tau bar. Question? No question. Okay, so these transformations will shift alphas by the z bar derivative of that. So it will be 2 pi I tau minus tau bar ni plus mi tau. So it is convenient to introduce variables xi, which are tau 2. Remember, tau 2 is the imaginary part of tau divided by pi alpha I. So these variables will be defined up to shifts by an integer or integer times tau. Okay, so that's just partially uses almost all of my gauge symmetry. Now we need to solve this equation with a bar of this form. So we do it analogously to the way we were doing it on the circle. So in the basis where a bar is diagonal, we look at the equations for the associated matrix elements of E. So when I is equal to j, the equation is simply that. So it says that the diagonal matrix element of E is holomorphic outside 0 and has only a pole of the first order. So the equation d bar equals delta function is solved by a meromorphic function of the first order pole. Now, this is the complexification of requirement that you have so this is it's a complex analog of the equation we solved, but maybe without paying much attention to it. So if you do it on a circle, the same thing. So you have so this is for comparison. You see, to have a pole in complex world is analogous to have a jump in the real world. So in the real world, this equation says that Eii is constant outside x equals to 0, and it has a jump. So the value, let's say minus 0 and plus 0, is equal to Jii. So if your function is a constant and has a jump, it means that the jump should vanish, right? So this is precisely analogous to the fact that if you have a function on an elliptic curve, it has only first order pole at one point. This pole has to be 0. The residue is 0, and the function is actually constant everywhere. So this is the complexification of that theorem. So Jii is equal to 0, and Eii, which I will call Pi, is a constant. Okay, now let's analyze what is Jii. So this is my matrix J, and so Jii is square root of minus 1 mu times Ziwi minus 1. And so this equation saying that this is equal to 0 implies that Ziwi is equal to 1 for all I. And now, just like on the circle, we have one more remaining, not one more, but we have other remaining transformations when G is diagonal T1, Tn, when Ti's are in C star. Of course, the product is equal to 1. And so by those transformations, I can make Z equals 1 and W equals 1. So now, let's solve this equation when I is not equal to J. So now things are interesting, because now outside the origin, the solution for Eij is simply the exponent. So it's minus Z bar alpha I minus alpha J. I can make it, to make my life slightly easier, I can put it Z minus Z bar here, times some function, let me call it L, Lij, which is only allowed to depend on Z. Now this function should have a pole of first order at 0. So Lij should have the pole Jij close to 0. And it should also have now some automorphic properties that, well, it should be periodic with the shift of Z by 1. And the shift of Z by tau should precisely compensate the non-invariance of this exponential prefactor. So it should be e to the tau bar minus tau times alpha minus alpha j. Now, what is Jij? Jij, now we simplified Z, is simply square root of minus 1 nu 1 divided by Z. So it's times 1 minus delta Ij. Okay, so these three properties fix L uniquely, and that's the Lax matrix. So Lij of z up to, so it's the theta, it's the odd theta function. Okay, so just like Andre, I will not write the argument. I will not write the subscript. It's the odd one of z plus xi minus xj, where x is introduced here, divided by theta of z, theta of xi minus xj, square root of minus 1 mu, and theta prime of 0, to make sure that the residue is the right one. Okay, so the new phenomenon is now that unlike the trigonometric case, when we had the analog, so this electric field E, which when you solve for it, it has the analog of this exponential dependence, but the prefactor, which was responsible for the Lax operator, essentially had no interesting dependence on the position of the circle. Now this function has an interesting z dependence, which leads to the following beautiful fact that okay, so first of all, so if I now look at E, the electric field, and compute its Casimir, well, okay, so the electric field itself has both z and z bar dependence, but the invariant, so if I compute the Casimir, actually has no z bar dependence. It depends only on z, and of course it follows from this equation. But it has a pole, so it's a meromorphic function of z with now second order pole at z equals to 0. Now the space of meromorphic functions which have a pole of second order at one point on the elliptic curve is two-dimensional. So such functions, all such functions have a form, the Weierstrass function, the function times some constant, plus another constant. And so this other constant, so this first constant is computable and it's proportional to nu squared. And the other constant is precisely the Hamiltonian, precisely this Hamiltonian H2. So now, if we go back to the large phase space, which was the space of E, A bar, and so on, and start the classical evolution generated by the Hamiltonian, which is the regularized kind of averaged version of Tracy squared. So essentially the second order pole, because it is meromorphic, allows the integral, the principal value integral of Tracy squared to be well defined. You see the function, so dz bar over z squared. So the principal value means that I'm integrating over the complement of a small disk, small round disk. So actually doesn't have to be round. So the fact that it has a pole is compensated by the fact that this, if I first integrate over the angles, I get 0. So singular part disappears. And so this is a well-defined Hamiltonian which defines a simple evolution on this infinite dimensional space of E, A bar, etc. And then we project by the action of the gauge group and produce the highly non-trivial evolution of this elliptic Calogero-Moser particles. So we can now exhibit the algebraic integrable structure of this phase space of the system using what we've learned, namely this phase space now has the structure of a fibration over n-dimensional base with fibers being abelian varieties. So these are the complexified, again, one of the possible complexifications of Liouville tori of real integrable systems. So what are these abelian varieties and what is this fibration? The fibration is defined as follows. We want to extract as much as possible from this electric field or from this Lux operator. And so the spectral invariants of this Lux operator will be conserved quantities because on this infinite dimensional space, any flow generated by suitably regularized Casimir of the electric field will produce a flow which commutes with the flow generated by Tracy squared, because anything which is built out of electric field Poisson commute with each other. So these are commuting flows, and because we're reducing by the gauge transformations which don't touch the spectral invariance of E, so that's the source of conserved quantities and the integrals of motion. But now, because we got something which depends on a point on the elliptic curve, the spectral invariants vary from point to point. So the object which is convenient to study is the spectral curve. So this is the set, the vanishing locus of the characteristic polynomial of L of z. So it's a curve which lives in, so where does it live? It lives, so we have elliptic curve E. We have the breadpoint z equals to 0 when L has a pole. So that means that, so over generic point of elliptic curve, this equation has n solutions. It's time, okay. But over point z equals to 0, something happens because L has a pole. And so, but the residue at this pole is the matrix of a special form. So it's a matrix which has, it's a difference of the scalar matrix and the matrix of rank 1. And so if you shift, well, there is a way to okay, I will not say it in full detail today. So there is a way to partially compactify. So this curve sits in the partial compactification of T star of E minus the point. So there is a little bit of blow up you need to do to resolve the structure near z equals to 0. And the point is that this is, so the claim is that this is genus n-1 curve, which essentially covers the elliptic curve. And so the Jacobian of, yes, sorry, and so it depends, so this polynomial, so this is a polynomial of lambda and the meromorphic function of z. So it's so as a polynomial, it has n-1 non-trivial coefficients. Each coefficient is a meromorphic function of z. There are only so many functions with the singularity at the point z equals to 0. So you can count how many parameters you actually have, and you get precisely n parameters. And so let me call them collectively u. So u. So these are the coefficients, the free coefficients in this polynomial. And so for any value of u, you have a specific curve, and its Jacobian is essentially the fiber of this fibration. So this Jacobian has it already has genus n-1. So there is one more missing, 1 degree of freedom missing, which is the elliptic curve itself, and which corresponds to the center of mass, which we discussed earlier. Okay, so this is only one of the many examples of integrable systems which have a Lax representation with the spectral parameter, and so I gave, in this case, I gave a gauge theory description of that. The other systems, which for example, the base curve, instead of being elliptic curve with 1 point, is genus 0 curve with many points, are also possible, and they are the complexification of the system, which you will get by marking several points on the circle. So starting the day after tomorrow, we will be describing a completely different story, which will start as a different story, which with origin in gauge theory, but the endpoint will be exactly that structure. So we will recover these integrable systems, both classical and quantum, from doing something like probability theory on some finite, or infinite, but filtered sets, and the asymptotics of the expectation values in this probability problem will be described by this system. Okay.
So questions?
Once we have this yellow formula on the board,
Yes.
so you can always stress the fact that this is his elliptic genus somehow connected. But I never figured, I don't know what is the.
Yeah, let's try to ask this question on Thursday, maybe. Yeah, maybe we'll get. Sorry. So the story which I will the story which I will present will recover this as a result of doing some limit shape computation in ordinary cohomology theory. So this is not related to the elliptic genus. So at least in the story which I know. So that story which I know has the elliptic version, but that ellipticity goes into the direction of the double elliptic system that Colli mentioned. So you see here the fact that the P dependence is rational has to do with the fact that this is related to the cohomology theory. If I go to K theory, the P dependence will become trigonometric. And if I go to elliptic, the p-dependence will become elliptic. But actually, calling this double elliptic is actually the wrong name. So people, I mean, I'm partially responsible for that. The truth of the matter is that once you start making both the fiber and the base elliptic, it's very hard to keep track of who is fibered over who. So in the simplest case, already the system of 1 degree of freedom n equals to 2, it turns out that the total space is the abelian variety, which is the Jacobian of a curve of genus 2. And so you can locally think of it as describing the fibration of one elliptic curve over another elliptic curve. So it has the moduli of both elliptic curves and the point on one of the curves, which describes how you shift over one curve and going around another. But it's not a globally it's not a global description. Globally, it's just the period matrix of the genus 2 curve, and which kind of emerges out of this structure. So it's and that's to be expected for high n as well.
Could you please repeat why a diagonal part of E should be constant?
Okay, just try to find the elliptic. Try to find the meromorphic function of the elliptic curve with a single first order pole. Yes.
So is this moduli space exactly the Hitchin moduli space on an elliptic curve with puncture?
With one puncture.
With one puncture.
With one puncture, with one minimal puncture. So technically, it's a minimal puncture. So the fact that the residue of L at this point is a scalar minus rank 1 matrix means that's what it makes it minimal.
For GLN, right?
Practically, Hitchin system is for any L over not elliptic curve, or curve of genus 2 and higher.
With parabolic.
Not practically, but technically. That's what Hitchin invented. But if you think, if you understand that Hitchin systems live in families over the Deligne-Mumford stack of curves, once you start the generating curves, you will get curves with punctures of lower genus, and that's what that's just. Okay, interesting things happen when you impose restrictions, right? So so if you so if you make J a generic orbit, then you will get L, which will have this factor, but it will also have a dynamical prefactor. So you will get what is called a spin Calogero-Moser system. And I mean, there is still some mystery here, which is what Alshonetsky and Perelomov discovered, that the systems make sense for any root systems. And of course, you explain this using kind of sophisticated algebraic structures. But there is no Hitchin system which will. So if you try to generalize this to other simple Lie groups, there are no orbits which will explain the Lax operator for other root systems. So Hitchin system is not the end of the world. So I put it this way.
Okay, more questions? I have a very short question. So there are these special connections that you threw away. When you modify this phase space,
right,
just as you did at the beginning, does it mean that you add them back?
You add some of them, yes, precisely. So in order to make the fiber compact, you need to allow for the situations where in the usual physics language, some of the particles run away to infinity, or they run through each other with infinite speed. And that is described by allowing for unstable bundles. So then what happens is what plays the role of the coordinate, this coordinate, actually loses its meaning because the associated component of the gauge field A bar now becomes a constant magnetic field, gauge field. So when you have a magnetic field, it means that this alpha actually now has a z dependence. It has a linear z and z bar dependence. The zero mode, which alpha is, no longer has a meaning. So I mean, I don't have the complete story there, but it's just the beginning.
Okay. Thank you. Thank you.